Welcome to the TCS seminar at Jagiellonian University. Today we have Raphael Steiner from ETH Zürich. Raphael did his PhD at Technical University in Berlin, and then you moved for a postdoc to ETH 4 years ago.
Roughly, yeah.
Yes. And today Raphael will tell us on longest paths and cycles.
Yeah, thank you, Vader. Okay, welcome. I want to talk about several results concerning longest paths and cycles in graphs. And basically the main motivation for the things I will talk about comes from a very nice old conjecture by Lovász that I want to start with. So Lovász made a conjecture about the Hamiltonicity of symmetric graphs, essentially. So let me quickly say, vertex-transitive graphs, this is what I will be talking about mostly now, is a graph where all the vertices look the same, essentially. So if you look at the graph from any vertex perspective, it will be looking the same way. In other words, the formal definition is that for all pairs of vertices u and v in the graph, there's a automorphism phi that sends the first vertex to the other one. Okay, so just any symmetric graph, like a cube, for example, or a cycle, that's what I mean. And for these graphs, Lovász conjectured that they are basically, that they should always have a Hamiltonian path if they're connected, which is of course necessary. So Lovász 1969 conjectured that every connected vertex-transitive graph has a Hamiltonian path. And why is this a remarkable conjecture? So somehow this stands a bit out in terms of Hamiltonicity conditions. If it were true, let's say, in terms of Hamiltonicity conditions that we know, because, for example, in fact, if you look at the literature of like conditions that guarantee that the graph has a Hamiltonian cycle or path, most of them, like Dirac's theorem or so, they require that the graph is very dense, so that you have vertices of degree that are linear in the number of vertices. And in fact, it's pretty stupid in the sense that like most of these theorems don't even apply to the cycle, which is the one graph that you really want to say is Hamiltonian, right? Like it's the definition, the smallest graph that's Hamiltonian. So it would be nice to have a very general condition that tells that the graph has a Hamiltonian cycle that also includes the cycle graph. And there's actually not many such conditions, so that's a quite ridiculous situation. And in general, we don't really understand what makes a graph have a Hamiltonian path or cycle. And in particular, this is a conjecture that, for example, allows very sparse graphs. So there's many symmetric graphs that have vertices, let's say, of degree 2 or degree 3, that they're free regular, for example. And that's why this is a very nice conjecture, because it describes a large class of graphs. If it's true, that contains many very sparse graphs and still guarantees Hamiltonicity in a non-obvious way. Okay, so that's why this is cool. Now, there's some funny facts about this conjecture. For example, it's not clear that this really was conjectured by Lovász in this form. I think in the original paper in 1969, this was asked as a problem, whether this is true. So it wasn't conjectured to be true, but over the years, now everyone seems to be calling it the Lovász conjecture, and it's like standard to call it like that. I will also do that. Mainly probably because no one has found counterexamples in many years. But then there's also some people who are not so convinced that this is true. So for example, Gallai, a bit later in 1992, I think, 96, he conjectured an opposing conjecture. He said that there exist arbitrarily large, or like let me say it like this, for infinitely many n, numbers n, there are n vertex connected vertex-transitive graphs. I will always write CVT for these things, so I don't have to write too many words. With no path longer than 1 minus epsilon times n for some epsilon. Right, so where epsilon is some absolute constant that's positive. So he says this is not only false, but it should be really false, like infinitely many counterexamples, and even separated away by some linear fraction from it. Okay, so he made his counter conjecture. That's obviously that's also very much open. So we don't even know whether we can always find in these graphs a path that's linear in length. So this is, yeah, any questions? Okay. These are these conjectures. I should also mention that, in fact, if you look at vertex-transitive graphs and also some small examples, then most of them seem to also have a Hamiltonian cycle, so not only a path. But why did I not write a conjecture that all vertex-transitive graphs have a Hamiltonian cycle? Because it's not quite true. So there are some sporadic, you could say, or we don't really know, but there are a few counterexamples to that statement that we know of. And of course, one of them, as almost always, is this famous Petersen graph. So Petersen is a symmetric graph. You can check that it's vertex-transitive, and it doesn't have a Hamiltonian cycle, but it has a Hamiltonian path. So this is one counterexample. There's also another counterexample that's called Coxeter graph. That's also a cubic graph. That's also symmetric, like Petersen. Also, sorry, it doesn't have a Hamiltonian cycle. And then you can get two more counterexamples by basically taking these graphs and blowing them up. So what do I mean by this? So if you have any cubic graph, you can do this operation of replacing all the vertices by triangles, like this. So you put 3 vertices in place of 1, connected by a triangle, and then they go to the previous neighbors, like this. And you can check that if you start from a graph like the Petersen graph, for example, which is not only vertex-transitive, but also edge-transitive, so every edge can be mapped to every edge with an automorphism, so all the edges look the same, then if you do this replacement operation, then the resulting graph will still be vertex-transitive. So if this was edge-transitive, then this is still vertex-transitive. So you can basically then start from Petersen, do this splicing operation, and also from the Coxeter, do the splicing operation, and then you get 2 new graphs that also vertex-transitive and are not Hamiltonian. Because it's very easy to see that, right? Any cycle in this graph corresponds to some cycle here. Okay. So these are basically the only 4 non-trivial counterexamples we know to the statement that every connected vertex-transitive graph has a Hamiltonian cycle. There's also some stupid ones like K1 and K2. They're just too small to have a cycle, but I think these are really all the counterexamples that we know. And therefore, there is some sort of folklore conjecture that's often attributed to Thomassen, that these are the only counterexamples to the strongest statement. Of course, we know even less about this conjecture than the other one because it's more difficult. Okay, so this is sort of the start of the talk. This is some nice problems that I really like and that motivate the rest of the talk. And what I mainly want to discuss a bit now is basically what can we prove currently about lower bounds for long paths and long cycles in such graphs. So I told you we don't even know a linear bound, and in fact it's even much worse. We don't even know a bound that's like n to the 1 minus epsilon for every small epsilon. And so I will talk about what we know there and some recent improvements. Also, some other things I can say about these conjectures. So there's a lot of work on these conjectures that I'm not mentioning now explicitly. For example, an important special case of vertex-transitive graphs are Gallai graphs. So you take a group, you take some generating set, and you connect any elements that differ by some generator. And these graphs, they're easy to see that they're symmetric. And so even finding these graphs, Hamiltonian paths and cycles is currently not known or a big old problem. And for many special cases of the group size or group type and the generator type, people know special cases where this is true, but it's nothing sort of very general. And people have even studied the setting of random Cayley graphs, where you take a random generating set, and people know if you take any group and you take at least some big constant times log of the size of the group, many generators randomly, then these graphs are with high probability Hamiltonian. That's a recent breakthrough. But yeah, so there's many open problems. Even, as I said, proving this for random Cayley graphs is open. Okay, but let's move on with the stuff I want to talk about. So in the following, I want to study, as I said, what is the best lower bound we can guarantee on the maximum path length in these vertex-transitive graphs. And there was so basically even proving some growing bound that grows with the number of vertices of these graphs on the length of the longest path or cycle is not completely obvious. And the first result in this direction was by Gallai from 1990s. Sorry, just a second. Where did I write it? 1979. Who proved that in such graphs you can always find cycles of length at least root of the order. So every and this is actually a very nice simple proof that I want to show you in a slightly modified form that I find convenient to present. It's a very elegant argument. So basically this whole proof boils down to one main observation that's very well known actually in graph theory, which is about how longest paths and cycles in a fixed graph, let's say connected graph, intersect each other. And this is some independent statements or like folklore statements. I will call them observations. And they will also connect to some other topics later in the talk. So here's an observation. So if the first one says if G is a connected graph, then any two longest paths in this graph intersect in at least one vertex. So if you take any two longest paths, then they overlap in some vertex. And analogously for two connected graphs, the same is true for cycles. Okay, and why is this true? So this is simple exercises that you probably have seen somewhere, but I will just quickly repeat the argument. So for example, suppose you have in a connected graph two longest paths, P1 and P2 here, they are, and they don't have any vertices in common. Then you just take a shortest path from some vertex here to some vertex here, some connection like this, maybe this one. And now you say, take the longer of those two halves of the path that to this endpoint cuts it in two, right? Maybe this one. Follow this path and take here the longer half, this other path, maybe this one, and together these two segments will already have at least the length of the original path plus something in between as a connection, so it's a longer path now. So that's a contradiction. And why do we assume this two connected thing here for the cycles? Well, if you just have connected graphs, you could have some stupid examples like a chain of triangles, for example, where no two longest cycles, which are the triangles in this case, meet each other. So you need some higher connectivity for the statement to be true. And so let's look at the cycle case. So if you have two disjoint cycles, if they are completely vertex disjoint by Menger's theorem in a two connected graph, you can find then two vertex disjoint paths between them, like this. And now you can make a similar argument to here to find a longer cycle. One nice way of seeing it, that's a bit of an overkill, but will be convenient because later I will do a similar argument, is to define two new cycles that together cover all the edges of the old cycles at least once and some additional edges. And when you can do that, then the sum of the lengths of the two new cycles will be higher than the sum of the length of the two old cycles. And therefore, one of the two new cycles will be an even longer cycle. So let's see how to do it in this case. So for example, you can say my first cycle uses this segment of that cycle and this segment of this cycle, as well as the connecting paths. And the other one just uses the other two segments and also the connecting paths. And so you can always define these two new cycles, the purple and the yellow, which cover all the original edges plus some new edges. So one of them now has to be longer. Okay, so that's why these statements are true, and that's a convenient way of seeing it. And now using these observations, I will now tell you a very short proof of this theorem of Gallai, how to find these root n cycles. So the idea is that we simply take along a cycle. So we take some now we simply, so let's say this is our cycle, and we simply map the cycle now with some random symmetry, so some random automorphism from the graph to some other cycle. So we take I in the automorphism group uniformly at random, and we consider the image of the cycle C by applying this automorphism. So this gives us a cycle that basically looks the same in some sense, and we know by I of C. It's of course still a longer cycle, it's at the same length. And now we know by this fact here, we have to quickly check why we have this precondition, but I will do this in a second. Then by this fact we will learn that these two cycles always have to intersect each other. Why can we apply it? So it's a well-known fact that any connected vertex-transitive graph with at least 3 vertices is also 2 connected, and the reason for this is simple. So basically, if you have any connected graph, then you can look at a spanning tree, and a leaf you can remove and you are still connected. So there's at least one vertex you can remove and still be connected, but all the vertices behave the same in a symmetric graph, so then you can connect. And this, right, you could remove any vertex then and not disconnect the graph. So this means that you're actually 2 connected. So you can apply this fact, so these must intersect each other. So we note that this implies that the size of the intersection between the vertex set of C and this vertex set of the random image should be at least 1. And phi is a random object, so we can take expectations from both sides, which tells us that 1 is the most expectation of this intersection side. Nothing to right. Anyway, but this is easy to compute, this intersection size, because you can compute it like this. So if you want to have a vertex in the intersection of those two things, then you must have someone here, right? Some vertex u in the cycle C, and some other vertex in the same cycle, or it could be the same, doesn't matter, such that this v by this automorphism phi now gets mapped onto this u. That's how you get an intersection between those two cycles, right? And the main observation is that the main property of such a random automorphism is that if you look at any one fixed vertex in the graph, then this image is distributed uniformly at random among all the vertices. This is because, I mean, basically you could, right, how to say, compose this with any automorphism that sends one fixed vertex u to another vertex v, so the probabilities of sending anywhere should be the same, or cannot be higher anywhere at one point than somewhere else. Okay, so this fact is all we need to compute this, because this means that the probability that this happens for one fixed pair of vertices u and v, that v gets mapped exactly to u, is 1 over n. And so the expected number of such overlaps should be the number of pairs of vertices we can take, which is like the length of the cycle square divided by n. Okay, now you rearrange this, and this tells you that the length of the cycle is at least root n. Another proof. So that's nice, I think. You can also look at this argument a bit better, and you can actually check that you can put a 2 here instead of a 1, and then you get slightly better constant and so on. People have observed these improvements, but this is not so, I mean, that's not a really road to go. So now what I want to tell you next is a recent improvement to this so long-standing bound of root n. So actually, even though this argument is very simple, this hasn't been improved in almost 50 years, this root n bound. And very recently, Matt DeVos presented an improved asymptotic lower bound that has a nice idea. So I will first now present this proof. And then based on the proof, tell you sort of, or talk about more ideas how we can further improve this bound. Any questions up until this point? Is something to dry, or I just ignore it? Okay, so let's see this next argument that gives us a better lower bound. And the lower bound we will get from this is the theorem of Lovász, is n to the 0.6. This is Lovász in 23. And that's really the first improvement that we have to this by bound since whatever 1979. So he proved that every such graph has a cycle of length into the 3/5. And Lovász basically takes the same proof approach, but there's sort of one new idea to it. And this new idea is that basically there's another way of viewing this argument here that is more general, and this is helpful to get the right perspective how you can find this proof. So here we said any two longest cycles must intersect each other. But another way of seeing it is that we found one cycle here that the set of vertices of one longest cycle is a hitting set for all the longest cycles in the graph. Okay, and in fact, if you repeat this argument that we did here in that setting where you have a set of vertices that's somewhat small that hit all the longest cycles, then you can also get a lower bound on the cycle length in the same way. So let me record this as a general fact that also will be needed later. So there's a simple lemma that you can prove the same way. We can discuss it in a second. It says if G vertex-transitive has a set S of vertices that hits all the longest cycles or paths. Then G contains a path or a cycle. Let's just put here connected to it. Of length at least number of vertices divided by the size of this hitting set. Maybe -1 for path because length is measured the number of edges, but doesn't matter. Okay, so the proof is exactly the same. So you basically just fix the longest cycle, you look at the random image of it, and then you compute the expected size of the intersection of this random image with your fixed hitting set. And it will be size of the hitting set times size of the cycle divided by n, by the same logic. So this should be at least 1, and then you rearrange, and then you get this lower bound. So having a very small set of vertices hitting all the longest cycles tells you that there must be a longer cycle or an analogously further path. Okay, so this is not even using this intersection property. Here the proof really basically says, in other words, either our cycle is already long, and if it would be short, then it would be a small hitting set, and then we would get a long cycle because of that. Okay. So this is a slightly more general observation, and you can also make it even more general, and this will be needed in this argument. Suppose we have in a symmetric graph a set of vertices that doesn't just intersect every longest cycle, but let's say it intersects every longest cycle quite a lot. At least some number of vertices, like x, right? Hitting all longest path cycles at least x times, where x is some number. Then G has now we can put here an additional times x. And the logic is exactly the same. Nothing changes. The only difference in this argument is that here in this lower bound on the intersection size, we will put x instead of 1, and then rearranging gives you this. Okay, so here's sort of then the game you can play. You can try to optimize the ratio between x and the size of the hitting set to get as long a path or cycle as you want. This is just all general observations, but it's good to make it general, then you don't have to sort of rethink this argument every time in the following. So this is the general observation. Now the strategy of Matthieu is the following. So instead of only looking at the fact that we proved here that any two longest cycles must intersect each other at least once, he looks at how much do different longest cycles intersect each other. So let's say K is the, let's do a proof. We define K as the minimum overlap between two longest cycles. In the graph, so C1, C2 longest cycles. Right, so this is something, it's positive, we know that, not much more. And basically now you think about two cases in your head. So either K is small or K is big. And both of the cases should be good for us. And for this, I have to sort of prove a lemma that I didn't tell you yet. So the case where K is very large is good because it means that, again, if I take one fixed longest cycle, then it hits every other longest cycle at least K times. So then in this lower bound, I can take x equal K, and it will push my lower bound ahead before from the Gallai argument. So if K is pretty large, then I just win over the Gallai argument by this fact that the longest cycle doesn't just hit everyone else, but hits everyone else quite a lot. Okay, but what if K is small? What do we do then? And this is sort of the lemma I was talking about. So there's a lemma that then guarantees that these two cycles, that if you pick two cycles that have rather few intersections, that then you can separate them in the graph by removing only few vertices. And this is a nice observation that then will give you another small hitting set in a different way. Okay, so this is the sort of the main new idea here. So let's say this also holds for general graphs. You don't need vertex-transitive. So the C1, C2 be longest cycles. Graph G. Such that overlap in at least one vertex. And we say K is the overlap. Then they can be separated by at most O of K square vertices. Okay, so this is the main novelty in the argument by Lovász. And the proof of this is actually surprisingly easy. So let's draw a picture that's supposed to illustrate this. So you have two cycles and then they intersect some number of times in different intersection points. Obviously, it will not look like this. It will be more complicated. And this intersection would probably be easy to handle in other ways. But let me draw this picture to explain what I mean. So you have these intersection points, and there's K of them. And then if you remove these intersection points from both cycles, they split into up to K connected paths, so it's connected components. So they will either be paths or empty, these components. So I can now, after I did this, apply Menger's theorem to say if I don't have a small separator between the remaining, right? So I look at the sets, vertex set of C1 minus intersection, and I want to go from there to a vertex set of C2 minus intersection. I want to send as many disjoint paths as possible. And by Menger's theorem, if I cannot achieve what I want in this lemma, then I will get order K square disjoint paths between here and here. Okay, and now I can look where are the endpoints of these disjoint paths, in which components of these that are left after removing the intersection points do these paths lie. So, I mean, just in your head, imagine like these are the up to K components of C1. Here are the up to K components of C2. And every path somewhere starts in one of these components and then ends another one over there, right? And the claim is that if you have more than K square of these paths, then you will get a contradiction. The reason is that by pigeonhole simply, there will then be one pair of a component here and a component here, where you must have two paths going between. right? There's k square pairs of components there and there. So if you have more than k square additional paths, there will be 2 additional paths like this. And now why is this nice? Because now I can win in the same way that I did over here. I think I can now also define these 2 cycles, maybe slightly differently, that then tell me that I get a longer cycle. And the reason is, so I define a green and a purple cycle. Both of them will use both of these middle connecting paths. And the first cycle will, let's say, not use this component, but travel the other way around the cycle, like this. And on the other side, I will just connect them directly within this component of C2. That's my first cycle. And on the other side, I do it the opposite way. So I also use these 2 things. Here I go the long way, I mean, just intuitively speaking. And here I directly take this connection here. And these are indeed cycles in the graph. That's very important because that's only a schematic picture, right? You have to be a bit worried about whether things are indeed cycles in such pictures if you somehow cross over several intersection points, right? Because then if you somehow cross over an intersection point on the left and on the right, then it's not clear that you wouldn't they wouldn't be the same point and you really would be a cycle. But the way we do it here, it's safe because right on one cycle on the one side we only use things from C1, and on the other side we only use internal vertices from one of these remaining connected components, so they don't touch C1 at all. So this is fine. So just to say what I mean, maybe say this more clearly again. When you have these components and they are arranged in this, right? They are somehow arranged along the cycle.
So you remove the intersection.
Yes, I remove intersections and then I get these components that I'm drawing here as these short paths. But they still, of course, have the cyclical ordering along these cycles C1 and C2. And what you have to be careful about when you define these cycles is that you don't, at the same time, cross basically an intersection point here and an intersection point here, because then there's no guarantee that they wouldn't be the same point and that it wouldn't be a cycle. You would only define a closed walk.
Yes.
But the way we do it here, we take care of this because on one of the 2 sides, the cycle only travels within the connected components, and these are free from any intersection point. Okay. Good. So why is this a contradiction, right? So now we have the same thing as before. All the edges are used, plus some additional edges, so one of the 2 new cycles must be strictly longer than one of the old cycles. So they couldn't have both been longer cycles. Okay, and this is the proof of the lemma. And now finally, why is this, so how does this give us a win, right? So there's, as I said, 2 ways to win. So let's do some small computation, maybe here, get some space left. Actually, let's look at the lemma because that's what we want to use. So there's 2 lower bounds we get on the length of the longest cycle. So let's say L is the length of a longest cycle. Then we know that this is at least by applying this lemma in 2 different ways, one of the following. So first of all, we know that if you fix one longest cycle of length L, then this is a hitting set of size L for all the other longest cycles and intersect every other longest cycle k times. So then I can use this lemma with size of S equal to L and X equal to K. So I get a lower bound of M divided by L times K. For the longest cycle length. And the other way I can win is I can look at this. So let's look at this picture with the 2 cycles.
So could you explain again this point?
Yes. So take one longest cycle. That the set of vertices will be your S.
The set of vertices will be okay.
And this set hits every other longest cycle at least k times by definition of k.
Yes.
So I can put X equal k here, and this will be L.
Yes. Okay.
So it's L over N over L times k. So that's what I said before, why we win over the by argument if k gets large, because we win this k compared to by only looked at k equal k at least 1 or something. And now, why do we win if k is big? So, if k is small. So look at the 2 longest cycles. We found some separating set between the longest cycles. Of course, it will not be disjoint, but let's draw it like this to explain the argument. So there's some separating set, let's call this S again, such that if I remove S, there's no path going from C1 to C2, right? Now look at any third longest cycle in the graph, or any other longest cycle in the graph. It must meet C1 somewhere, it must meet C2 somewhere, so it must also go through the separator.
Yes.
So S, together with the intersection points of C1 and C2, this set, which is of size O of k square, is a hitting set for all the longest cycles. So then we apply this lemma only with x equal 1, but size of s equal O of k squared. So we get n divided by k squared basically. I will ignore the constant vector here.
So with S together with 1 is a hitting set?
You also need to include the intersection points of C1 and C2, which are k, because right enough.
Is it continuous?
No, because I mean maybe no, because I look at the separator between those sets.
Oh.
Maybe you're right, but could be, yeah. Anyway, it doesn't matter. It's a difference of k, so I didn't really think about it in my head. You could be right. It must be contained. Okay. So now you can optimize these numbers and do these cases when k is big, k is small, and you will see that this always gives you that L is at least n to the 0.6. This is just a simple computation which I will omit. But it's clear how we gain, right? If k is very small, this is almost n. If k is big, we win over the bubble. Okay. So that's a very nice argument. And I wanted to explain it because this will be the basis of further improvements that I now want to explain. So with two groups of operas, we sort of looked at this, I mean, starting from Nettebuss's proof, we tried to make further improvements to this lower bound with some success. And the first idea, that's maybe the most obvious, how to improve this lower bound on the cycle length, will be to improve this lemma. Because it's not obvious that this lemma is tight, right? So you have two longest cycles in any graph, with k intersection points. What's the best upper bound you can give on a separator between the cycles in terms of k? And of course, the cycles could be exactly the same cycle of length k, for example, or like then you cannot improve this lemma to better than like linear in k, in general at least for graphs. But this is still a long way. And for example, if you would put O of k here as a linear bound in k, then you would get n to the 2/3 of the same argument, which is significantly better. So this is what we were fighting for, trying to put a smaller number here. And so let me first talk a bit about this now. And then later I will talk about a completely different approach. But that's what Any more questions? Anything up here? So I want to now talk about how one can improve this lemma. And the main result that we have there with, I wrote it down so I don't forget someone. This is from Gallai Grönland, from long break, Jeremy Kot and Liana Yepremian from last year. So we get a bit of an improvement to this lemma. We get an upper bound of O of k to the 8/5, which is 1.6 in the lemma. This isn't quite what we want. We can still have hope for a linear bound, but we at the moment don't know how to prove anything better than this.
Did you forget yourself on the list of numbers?
Yeah, sorry, actually, of course. I don't know where. Anyway, doesn't matter. Okay, so yeah, so this is the upper bound that we proved, and actually, it's the approach that we took is very simple in some sense. It's a computer-based approach, so it's nothing like amazingly clever. But I think it's still it's nice that you can reduce this problem of improving the bound on a lemma to essentially a finite problem, and it's not completely obvious. So let me tell you how to reduce, or how I can use finite computations to attack this problem. So yeah, let me draw a picture to explain this again. So the idea is a bit similar. So we again look at the setup where we have these two longest cycles, and we look at these components that we are left with after removing the k intersection points. And I always draw this like this. I mean, in my head, I always assume that this is like a cyclical ordering of these things goes like this and like this, right? And now, of course, we can again apply Menger's theorem. We get this path family and so on, and we want to bound how many paths we get, right? This is what tells us the separating size. And now, the way to formally look at this is that you can make an auxiliary bipartite graph where you connect a path segment here to a path segment here if there's a path in this family traveling in between. And this is actually makes sense as a graph. It's a simple graph by the argument of Matt DeVos. We cannot have multi-edges in this graph. So basically, our goal is to bound a number of possible edges in a k by k bipartite vertex bipartite graph, which has the only restriction that it cannot, that whenever this kind of pattern appears, then we will find a longer cycle. But this is a very strange condition, right? So basically, you can look at a class of bipartite graphs that's hereditary, that's closed even under this monotone, even as.
So wait, whenever we hit the graph, and what are you looking at?
Yeah, so let me try to say this more precisely. So I look at the class of graphs of k by k bipartite graphs, such that when in such a picture, I mean, it's hard to define this, but this is also not how we define it in the paper, but this is intuitively what's going on. That if in such a setup where you have two longest cycles and these components, and sort of there is a graph isomorphic to this pattern that with the paths, right? So this auxiliary graph that we define with this path family looks like the graph in our class. Then this graph so such a graph belongs to our class if it is allowed in such a setup. So there are certain patterns that if you have them, for example, this multi-edges, then you will be guaranteed to get a long cycle. So there are certain, and we're looking for the graphs that can be put here without the fact that we can guarantee a longer cycle.
So I have a question.
Yeah.
Is it okay that you ignore the ordering of attachments on the smaller path? Because like they have a smaller path.
No, we will not ignore this. So so you're right. We can also keep more information. We will do this, but for the moment, I just want to say sort of what the problem is, right? So the problem is we want to bound we want to give the best possible upper bound on the number of edges in a k by k bipartite graph, which somehow can appear in some permuted way in such a can be reflected by such a path family. Okay, this is really you could define a class of graphs that's monotone in a weird, complicated way in such a setting. This is some monotone class of graphs, and we want to say what is the extremal number of this class. That's how we think about it. Now, of course, then when you want to understand what are the graphs in this class, then you have to think about these things again and do longer paths and so on, longer cycles. Okay, so what was our approach to this, and why can we do this with a computer? Well, one way to upper bound the number of edges in graphs is to use extremal graph theory and to find forbidden patterns. And basically, you can look for things that are not in this class. So look for patterns that will guarantee you a longer cycle. And if you find such a pattern, then you know the graphs in this class that we care about will not contain it. So then you will get an upper bound on the number of edges of this graph in terms of the extremal number of this forbidden configuration. And you can try out different things here because there's many results in extremal graph theory that we know and then hope that they don't appear here. And let me say, for example, what is maybe what was already done before in the literature and what one can reasonably try out. So the first, so actually, here's maybe I should say the history of this. It's a bit more complicated. So before we did this work,
basically whatever pattern you find, you already improve the quadratic upper bound. Yes, because
it must be a bipartite graph.
Because extremal number of every bipartite.
Yeah, that's true. That's true.
Okay.
But that's already non-trivial. Okay. So, but let me say what was known there. So, obviously, the largest bipartite graphs that you could try to forbid are complete bipartite graphs, and we know they're extremal numbers, or at least we know good upper bounds. And in fact, there was already a paper that was overlooked by Matt DeVos in his argument completely from 19. Okay, so there was a paper, a theorem, let's say, by Chen and Gold from 1997, I think. and it says that doesn't quite address the setup, but basically if you look into the proof, how they prove it, it would address the setup. So they didn't care about this special setup. They proved the following formal result, that in a k-connected graph, let's maybe not call it k, in a s-connected graph, any two longest cycles meet in at least omega of s to the 3/5 vertices, if s is at least 2. So we already know that in a two-connected graph, any two longest cycles must have at least one vertex in common, and there's a problem in this direction. There's actually conjecture. You have another conjecture by Smith from 1984, which says that this statement that they are proving here can be improved to simply S. It's a very nice conjecture that's wide open. So the statement of this conjecture is that the same as above, but that these things must meet in at least these S vertices. So this was the conjecture that motivated this paper. They were thinking in this setup, they were thinking about highly connected graphs. And then in this setup, they were observing that you can prove this lower bound on how much two longest cycles must intersect. And that, by the way, is still wide open. So I will come back to this later. But if you don't think about global connectivity, but just local connectivity, which is what we have here between the two cycles, then their proof actually does work exactly the same way. And they did follow exactly this approach that I was outlining here, that you try to find a forbidden pattern in such a path family between two long cycles. So what was the forbidden pattern that they found? So this is proved by showing that the graph K3, some one with many zeros, some large number, doesn't matter, is a forbidden pattern, or is a forbidden subgraph for this family. Okay. So how can you prove this? So the main idea that comes into this proof is that there's the following observation that now comes back to these kind of pictures. Maybe let me draw it there. So one thing that, which is an example of a configuration such a picture that gives you a longer cycle, is the following special type of a C4. So suppose you have two segments here, and now you have a nicely ordered C4. So you have a path here, and then the other paths cross like this. And it must be that your endpoints are exactly ordered as I've drawn here. If you have this pattern, you can again see that you can define two new cycles in this graph in the same way we did in this proof, that are actual cycles, such that they together cover all the edges of the old cycles and some new edges. Let me maybe give an example, or let's do this example together to get some feeling for it. So I think the first cycle goes on this side only via the short, on the right side only via the short edges, and on the other side sort of via the crossings. So let me draw it. So here you always go via these connected components, and here you go via the rest, and symmetrically here, right? So all these middle edges are used by both cycles. Here you go the long way, and here you go the short way. Okay, so this is an example of a configuration in this picture that would give you a longer cycle, especially ordered C4. Now, what they did in this paper is they realized that you cannot just get this C4 straight up, so we cannot simply say that there are some other C4 orderings that are not good, that would not allow you to do these cycles. But they showed that if you have this as a subgraph, then no matter how you, in this auxiliary graph that I defined as bivalent graph, no matter how you order the endpoint of the paths by some Ramsey and pigeonhole type arguments and adder signals and so on, you can then always guarantee such a specially ordered cycle, and therefore find a longer cycle in the full graph. And then you look at the extremal number of this K3 1000, and the nice thing with extremal numbers is that this doesn't change the order of magnitude of the extremal number. This second thing I put there, only the smaller of the two numbers matters. And so this only changes the constant factor essentially, and this will give you still the same as the extremal number of K33, for example, which is of order n to the 2 minus 1/3, so this is n to the 5/3. So basically they would get a separator of order k to the 5/3, which is a bit worse than what we have. So pi third is 1.666, and we get 1.6. So our improvement in that sense isn't as great as it initially seemed from k-square to this, but in fact, Matt DeVos missed this in-between step that already existed in some hidden way in this other paper. Okay, but anyway, this is a systematic thing that can be studied, and so there's probably more to be done in this problem. So what did we do to improve this problem further? Well, we found another subgraph. So in fact, we showed two things with a computer search, and I will be a bit short here because this is nothing I want to talk too much about. It's a lot of programming and implementation, but basically you can, it's not so hard to convince yourself that if you find, or if you fix a finite graph, right, for example, a graph on 10 vertices, then there's only finitely many ways how you can put it into this picture, because there's only finitely many ways how you can decide which vertices go to which of these intervals here, and only finitely many ways how to commute the endpoints of the path here. So there's lots of ways, but finitely many. So here we took a computer, and basically you can try to brute force through all these configurations, and then you will actually fail, because it turns out that this trick that we are doing here of trying to find two such cycles that are actual cycles that together cover all the old cycles and some new edges doesn't always give you a win. Not at least for the patterns that we looked at. But there's more tricks you can play. And if you want to be really sure that you sort of make sure that you can, whether or not you can guarantee a longer cycle, what you can actually do is you can do linear programming. So suppose you fix the pattern, like for example this one, and you want to find out does this guarantee a longer cycle or not. Well, you can simply put sort of lengths or like weights that are at least one on all these possible segments that appear in this picture, all the edges and subpaths, and then say using linear program or using linear inequalities, a linear system, you can determine whether or not it is possible to put weights in such a way that these two cycles on left and right are the longest cycles, and there's no other longer cycle.
But you put weights on these, the left cycle and right cycle, the edges in between are supposed to be short, I guess, right?
So the edges in between, all we know about them, they have length at least 1, so we put in the constraint that these variables on the middle are at least 1.
Yes.
For all the other ones, I think you just put that they're at least 0, and then you want to say, so you fix that the length of the left and the right cycle is exactly 1, that's your, you scale it to be 1 as a maximum, and then your constraint is that for every other possible good cycle is someone that really gives you an actual cycle in this picture and doesn't create a closed walk intersecting itself. You have the constraint that the sum is strictly less than 1, basically, at most 1, and basically you want to figure out the feasibility of such a system. Did I say it right now? Yeah, I think it should, yeah, that should make sense. Yeah. So if this system is feasible, then it's not possible to deduce from this pattern that there is a longer cycle, but if it's infeasible, which you can do in finite time using programming, then you know that this pattern guarantees a longer cycle. And we looked at pretty large graphs, so it was necessary to do this. And just to say that this simple trick with 2 cycles didn't always work. Sometimes you needed this linear program, which essentially means that maybe you don't find 2 cycles covering all the old edges, but maybe 4 cycles that cover all the old edges twice or something like this, right? So this could be another way to win. Anyway, so what we showed was that, in fact, computer search and LP that K33 already is a forbidden subgraph. This doesn't help you much because this only changes the constant factor, but it's interesting to know. And a certain graph that we call Q3 plus are forbidden subgraphs. And what is Q3 plus? So Q3 is simply the cube graph, so it's just the skeleton of the cube in 3D, bipartite graph like this. And Q3 plus is still a bipartite graph where you take two total vertices of the cube, like this one and this one, if you imagine it in free space, and add a new edge there as well. And it turns out that, for example, if you only take Q3, then our computer-based approach told us that this does not guarantee a longer cycle, but with this additional edge it does. So it's a very anyway, then we were lucky that in the literature there's a nice result by theorem by Erdos and Simonovitz, which tells us that the extremal number of this graph, they look at have a paper about the extremal number of this graph, and they prove that it's at most what we put up there, k to the 8 over 5. They proved that extremal number of this graph is at most n to the 8 over pi. Okay, and of course we could extend this computer search, try to find better graphs and so on, but it doesn't seem easy also because, as I said, there's super many configurations of this type and the computational power is limited to some degree if you don't have more ideas. And probably if you want to improve these bounds further, now the next step would be to, instead of trying to do this computer search, to really go into the structure of this graph class and understand something meaningful about it. But that seems still difficult. I don't have good ideas at the moment.
Could it happen that if you exclude both of these graphs, then your external number is even smaller?
Yeah, that's a very good question. Excellent. We even addressed it in our paper. So probably not. And the reason is that there's a conjecture by the same two authors, Erdős and Simonovic. And the conjecture says that if you look at the extremal number of, if you exclude any finite list of graphs, then this is up to constant factors always determined by sort of the best graph. Right? So if you have, for example, here K3, which has extremal number n to the, what did I say, 5/3, which is worse than Q3 plus, which has n to the 1.6 at most, then up to constant factors, the extremal family, when you exclude both of them, will still be determined by the better one, by Q3 plus. But this conjecture could be false. Could be false. Could be that both of them help you, but this is another conjecture that's would be even bigger to address probably. So anyway, that's a good question. Okay, so this is what I wanted to say about this first approach. Now let's see how much time did I use up so far.
Oh, you have time.
Good. So now, so anyway, let's keep this proof here because I want to now go to the second. Sorry, I didn't quite conclude this here. Let me just quickly say what comes out of this when you now plug into the numbers again into these lemmas and so on. Then what you get is for Lovász, you get a lower bound for longest cycles of n to the, it's not much better than what Matthew got. It's the 13 over 21 as a ratio, which is roughly n to the 0.62. So I mean, there's still a long way to go. For example, if you, I already mentioned this, if you would solve this problem to the maximum, if you would get a linear bound on the separator in terms of k, then you would get n to the 2/3 here, which would be 0.666. So even this would not solve Lovász, wouldn't even be close. But anyway, it's a very long-standing problem, and this root m bound, for example, wasn't true for 50 years. So at the moment, I'm sort of quite happy with any progress, and it doesn't seem very easy. Okay, so that's the first thing I wanted to say. And yeah,
just a comment.
Yes.
Because, a long time ago, I was working on some online game.
Yes.
And the value of that game had the golden number as a multiplicative factor.
I see.
And the way I got there was that I was approaching strategies from both sides, taking the fraction of two consecutive Fibonacci numbers. Okay. And two of all your exponents are fractions of
really?
Fibonacci numbers. Like 3/5.
Yes.
8/5. 13/21. 5/3.
I didn't notice that. There will be one more coming. Let's see where. I don't think it matches your pattern, but
yeah, sure. I mean, it's just.
It's funny, yeah. I agree. Okay, good. So let's keep this because this is the motivation for the next thing as well. So next, I will talk about something that seems a bit different, but then later comes back to these conjectures and will give us another improvement. But I think, yeah, what I will next tell you about is independent for its own sake, interesting for its own sake. Also, this problem here, sort of that we study here, is interesting on its own sake, not just for improving the Lovász bound, but also for improving the Smith conjecture, right? So that I mentioned that. How many intersections can you guarantee between longest cycles in a highly connected graph? There we also slightly improved the bound. But anyway, so now let's talk about longest path in cycles in general graphs a bit more. So I will go a bit away now from this, for the moment, from this vertex-transitive setting, and instead try to bound these hitting sets for longest paths in cycles that we talk about, for example, in this lemma, for general graphs. And there's many nice questions also about this. So let me make a next caption. So longest paths and cycle transversals. That's how they are called in literature if you want to search for them. So I prefer the word hitting set, but in the literature these are classically called transversals. So let me make one quick definition, and I can write this down more quickly. So LPT of a graph G and LCT of a graph G, these are simply defined as the smallest number of vertices contained in this graph, which intersect all the longest paths or all the longest cycles, and the T is for the transversal. Minimum size of a set S of vertices, and S hits all the longest paths. And the same here for cycles. Okay. Okay, and what does this lemma here tell us about the relationship between Lovász conjecture and these quantities? So this lemma tells us that if G is connected to vertex-transitive, then G has a cycle or path, or let's for example say a cycle of length at least, and divided by LCT of G, and analogously for paths. And therefore, if you could, in general, for any graph, basically, connected graph or two-connected graph, give good upper bound on these two quantities, LPT and LCT of G, then you would also get interesting lower bounds for Lovász conjecture. And this is something that isn't well understood even for general graphs. In fact, as I will tell you in a second, it's even possible that for every connected graph, for example, this LPT of G is bounded by a constant. This is, as far as we know at the moment, not ruled out. In which case, this would give you a linear lower bound for the length of paths and cycles in vertex-transitive graphs. So this would be much better than what we currently are doing. But this is, for now, out of reach, and I want to now tell you what do we know about these problems of bounding these things. And not as much as we would like to at the moment, but it's still a very interesting problem to study. So let me start to motivate this a bit more from some question of Gallai. This is a question asked in 1966. And the motivation for this question was this observation that we had at the beginning, that in a connected graph, any two longest paths intersect somewhere in a vertex. Now, going from this, it's very natural to ask, is it also true that in a connected graph, do all the longest paths at the same time? If you take intersection of the vertices of all the longest paths, is this non-empty? Is there a vertex that sits in all the longest paths at the same time? That was the question. So in other words, with this notation, I can also phrase this as saying that the LPT of G is equal to 1. Right, so if this were true, of course, it would even imply Lovász conjecture. But turns out it's false. So there were pretty quickly some constructions of some smallish graphs that don't have this. And for example, this is an example, I can quickly draw it, found by Walter and Santirescu a couple of years later. So you have like this triangle, you subdivide it, and then have some connections like this. And you can check that there's many different types of longest paths in this picture, and there's too many different types that you can hit all of them with one vertex, basically. I mean, that's it. And this graph is in some way derived from the Petersen graph, so it somehow relates to the Petersen graph again. So it's not surprising, maybe, because Petersen also doesn't have a Hamiltonian cycle, and it somehow connects a bit to that. In fact, if you want to see an example of a two-connected graph that doesn't have LCT of G equal 1, which is an analogous question you could ask for cycles, then this is easier, similarly simple, but even easier to answer simply by saying, I look at the Petersen graph again, right? So Petersen, it has doesn't have a Hamiltonian cycle, so the longest cycle, in fact, you can check it, this is exactly one vertex in this graph. And because it's symmetric, then for every vertex, if you remove it, there will be one cycle that covers exactly all the other vertices. So then the intersection of all the longest cycles is empty. So yeah, so there are these two examples that were pretty quickly found. As I said, I think this is due to Walter and Santirescu. that we need at least two bounds for an upper bound for general graphs for these two parameters. And it's actually not so easy to get my first example. So a bit later, Grünbaum looked at this question, and Grünbaum proved a low amount of 3. So he had a more complicated construction that I cannot draw because it's too big. 1974, he proved there are graphs G such that we connected such that the LPT is at least 3. Or, I mean, for this example, it will be exactly 3. And an analogous thing for 2 connected. So for both hitting longest paths and cycles, you need sometimes at least 3 vertices. That's all we know. And in fact, this is now, you can check it, right? This is more than 50 years ago now, this result. Since then, no one has found a graph that needs more than 3 vertices to hit all longest paths and cycles. And that's a crazy question. So if you want to think about it, I invite you to do it. It's somehow mysterious and magical. If it would be 3 always, I don't really believe it. And even the much weaker question is that I mentioned before: can we upper bound LPT and LTT by a constant, universal constant, for all connected or respectively 2 connected graphs? That's also open. So there's a problem of right answer. Let's go. Right, so these questions have been explicitly asked in literature around the same time. So this is very old questions that we don't have any clue about at the moment, at least not from this lower bound side. So we don't have any good lower bound. And therefore, maybe one should, if one believes that these numbers should be really small in general, then one should maybe try to at least find some good upper bounds for these parameters. So now let's look at upper bounds. Now I can remove it. So how can we upper bound the number of vertices in a connected graph that hit all the longest paths or cycles? And it turns out that this problem seems to be difficult from both sides. So like also the upper bounds that we currently have aren't amazing. So this problem in particular with the constant remains open. So all the upper bounds we have at the moment, they need to depend on the number of vertices of the paths that we look at. And there has been recently some work on improving these bounds. So here's a list of partial results. So the first non-trivial results was by Rautenbach and Sereny, 2014, and they show that, okay, let me abbreviate this a bit. So when I say, let's define this maybe quickly. So P of n, let's say, is the maximum LPT of G if G is connected and has n vertices. And C of n is the same thing for 2 connected graphs and cycles. And then I can say these things more easily. So they prove that P of n is at most roughly n quarter, and C of n is also at most roughly n quarter with some, at most n third, with some asymptotically sublinear minuses here that I will skip. So even this is not completely obvious to prove. So I mean, even a linear bond. But soon after, there was some sublinear bound, so that at least is a little O of n. So this was by Long, Milans, and Morano. They pushed these bounds both to O to O of n to the 3/4. That was the first improvement of the exponents in some sense. And then this was further improved by Kierstedt and Renn. Sorry, I forgot to write the numbers. This is 21. This is 2023. This was further improved to something like O of n to the. Sorry, this is into the 2/3. And what I will show you now is a theorem that says it's joined with Sergei Norin, Stefan Thomassen, and Paul Wallen. Right there. That you can improve this to roughly root n. Still far away from the constant bound, but at least root n is somehow a nicer number. And for example, recovers the Babai argument. If you just do n divided by root n, you will get root n back. But of course, this is a much harder problem to upper bound this LPT and LCT than, you cannot use Babai's trick to do that because it uses this covering of longest paths and cycles with multiplicity, while here we want to cover every, here we cannot use multiplicity in these problems. So this is something I want to talk more about. And this is, I think, a very nice proof. Let's see, I don't know, how many minutes do I have left? Can I sketch the argument? Okay. So, how many minutes roughly is it? I can
15, 20.
Yeah, okay, I think I can do at least, it should be enough for a sketch, definitely. Okay, so, how does this proof go? I think it has a nice idea. So, basically, we start from the fact, let's maybe do cycles. Cycles are, in fact, a bit easier for this proof than paths. So, let's say we have a two-connected graph, and I want to find a hitting set of size root 8n that hits all the longest cycles. So what do we know about longest cycles? We know that they pairwise intersect. So if I take any one longest cycle, it's a transversal for all the other ones. So in fact, I can always find a cycle that hits all longest cycles. So I can also pick a shortest cycle with respect to this property. So take a shortest cycle which has a property that intersects all the longest cycles. This, starting from this setup, is actually the main idea of this proof. So pick C shortest such that C intersects all long cycles. Okay. Now I claim that this cycle has some really nice properties, or otherwise we're done. In fact, I claim that we can assume that the cycle C is geodesic. So what does geodesic mean? If I have a cycle C that lives in some graph G, right? Then I say that it's geodesic if essentially there's no shortcuts in the graph through C. So a shortcut would be some connection like this, where this path here is shorter than both segments along C. Or a formal way of defining it is that C is geodesic if the distance along C between any two vertices is exactly the same as the distance in the whole graph. Okay, so it's like a metric subgraph or something. And okay, so why I claim that we can assume that this is the case, or otherwise we're happy. Okay, so I'm not saying this is like formally a contradiction if we don't have it, but if I claim if it's not geodetic, then we will already more or less directly get this bound. So let's first do the case that it's not geodesic. So then it means that there is this shortcut somewhere. So there's this path, let's say P. We can actually assume, this is easy to see, that it's even internally disjoint from C, so it doesn't intersect more than twice the cycle. Such that these 2 points X and Y here, they have, shorter distance along P than along the cycle. So this cuts the cycle into two pieces. We can define a new cycle C1 that uses this segment of C and the path, and another cycle C2 that uses this segment of C and the path. And they are both strictly shorter than C, because the path is strictly shorter than the connections in the cycle. Okay, and because they're strictly shorter, this means that both C1 and C2, by our assumption, do not intersect all longest cycles. Okay, so there are some longest cycles, L1 and L2, let's say, or let's call them like this. Picture a bit bigger, so there's some longest cycle here, L1, some other longest cycle, L2 here. And of course, I draw things disjoint, but actually they're not, but it's easier like this. You cannot draw a picture where everything intersects each other. Such that C1 is disjoint from L1, and such that C2 is disjoint from L2. That must exist. And now I claim that we can use this to get a nice hitting set. And for this, I need to tell you one general fact that holds in general. So look at any pair of some cycle with no restriction on its length and some longest cycle that's disjoint from it. Let's look at this setup for the moment in general. So some cycle like the C1, for example, and then this disjoint cycle L1, that's the longest cycle. And let's say L1 has some, L1 has some length L and certainly not bigger than M. But for later purpose, let me record this. Okay, and anyway, the idea is that in such a setup, I can always separate this cycle C1 that's disjoint from this long cycle by removing only, so I can find a separator I claim, by using only root of the length of the longer cycle vertices over root L vertices. And why is this the case? So it's a similar trick as we have here. So suppose not, then we get by Menger's theorem roughly root L vertices and paths between those cycles, right? And then you can look at the endpoints of these paths on this cycle L1 of length L, and it will tell you that because you have root L of them, maybe you want to put some constant here to be sure that everything works, but probably not. It means that two consecutive, like you look at the consecutive endpoints here along the cycle, and two consecutive of them must have distance on the cycle at most roughly root L, L divided by root L. Right, so look at two such things, like maybe X and Y here. Then you can try to make the cycle now longer by going from here along this path to this short cycle and to this short cycle. And now you can try to augment, try to continue either along this side of the cycle or along the other side. One of the two sides will be at least the length of C1 divided by 2, right? So the way we can, so we would get a contradiction unless C1 is roughly of length at most root L. If C1 is significantly bigger than root L, then the longer of these two segments that connect these two endpoints will add us, let's say, more than length root L to this cycle, and we lost only roughly root L by ignoring the segment between X and Y. Okay? So C1 itself cannot be longer than roughly root L, but well, then C1 itself is a separator from C1 to L1. Okay, so this is basically how this argument proceeds. So either C1 is short and then we're anyway done, or if C1 is long, then it will help us to get an extension of this long cycle. Okay, so let's apply it back to this picture. So we know now that there's a set S1 of size at most root L, and so in particular root N. This root L comes later. For now, we don't need it. Between C1 and L1, and a separator S2 of size at most root N between C2 and L2. And now we take the union of these two separators, still of size at most root N, and this gives you some constant factors. If you optimize it, you get this root A. And I claim this is the longest cycle transversal. Every long cycle must meet S1 or S2. Why? Because every longest cycle must intersect C by our choice of C. So it has to intersect C1 or C2. And it must intersect both L1 and L2 because these are both longest cycles. So either it has to go through S1 or through S2. Okay, so this is a nice way how to get it. It must be a geodetic cycle. Now, of course, the big question is, what do we actually do with that if it is a geodetic cycle? So how do we get a root N there? And there I have to state one more theorem. It's actually kind of surprising that it comes in here. That's from the graph minus series of Robertson and Seymour.
So where did you use that?
That what?
That is not geodesic. Where did you use it?
To get a path P. P is shorter than the both segments along C1 and C2. So C1. So this guarantees that C1 and C2 are strictly shorter than C.
And since they are strictly shorter than C,
they are not longest cycle transversals. That's how we get L1 and L2.
That's why okay.
Right? So otherwise you wouldn't get any of this.
Yes.
So the fact that P is shorter than the connections between the endpoints on the cycle guarantees that C1 and C2 are strictly shorter than C. That's why our choice of C mattered. That's how we chose it. Okay, so now here's our C, and we know it's now geodetic. Geodetic, we said geodetic, no, doesn't really matter. Okay, and I claim that such a cycle cannot have what is called a large transaction. And this is a notion that comes from the Robertson and Seymour graph minus series. So I have to make some definitions briefly, but these are simple definitions. So let's say I have a graph and I have some subset of vertices in this graph that is cyclically ordered, and it doesn't have to be a cycle in general, but in our case it will simply be the cycle. So this is called a society in a graph. Don't ask me why, but this is what they call a society. So this simply is cyclically ordered subset of vertices in a graph. And now a transaction in such a society is the following. So you somehow divide the cyclically ordered subset into two segments. Let's say A is this circular interval and B is this circular interval along the cyclical ordering. And a transaction is any family of disjoint paths such that every path goes between A and B. Like this. Right? And these paths all are internally disjoint from the society, so they just start there, then they go out and they come back in. That's how you can imagine a transaction. Any disjoint path family such that we can cluster their endpoints into these disjoint subintervals A and B. Okay, that's a definition. And Roberts and Seymour, for this graph minor theorem, the structure theorem, they needed a result about such societies that do not have a large transaction. What structure does this give us? And they have a nice theorem that says the following. If so G and some subset omega that's cyclically ordered, that's how people denote a society, does not have transaction of order K, say again? Yes, exactly. Then it has what they call a linear decomposition. I will explain in a second what it is. With adhesion, I will also explain what it is. At most 2K, something like this. Okay, so what is this decomposition we get? And let's directly apply this maybe. Anyway, let me try to draw it in this picture. So you look at the largest transaction you can get in such a society. It has some size K, and now their result tells us that we can structure the whole graph in a specific way. So what do I mean by this? So usually a path decomposition is simply that you have like a linear layout. It's like a path, like a tree decomposition, but with a path. And then you have sort of these bags that correspond to subpaths. And basically, there are some conditions on how the graph relates to this picture. So how to say it? So for every edge, there is sort of in the graph, there must be a bag that contains both endpoints of this edge. This is as in a tree decomposition. And if you look at, so, sorry, I explained this badly. Let me do this once again. Okay, so normally a path decomposition is defined as follows. So you have a graph, and you take a path, and the path doesn't have to relate to the graph directly in any way, right? And now for every vertex of this path, you have some specific subset of G that's called a bag. And now there are some rules of how the vertices of G have to be represented in this picture and the edges. So if you look at one fixed vertex, then it must appear somewhere in this picture in one of these bags. These are subsets of G. And the subsets in which it appears, they form a subinterval of this path. It must be consecutive somewhere. Every vertex, if it appears here and here, must also appear everywhere in between. That's the first rule. And the second rule is that for every edge, x, y in the graph, there is some bag that contains both endpoints of this edge, x and y. That's a path decomposition. That's it. And the adhesion of a path decomposition is when you look at the overlap of consecutive bags. So if, for example, you have, so another way to draw this picture is maybe that you think of your graph decomposed into subsets of vertices that can overlap, like this. They could overlap more heavily than I'm drawing here. These are these bags, and the adhesion of such a path decomposition is simply the maximum size of the intersection of two consecutive bags. And why is this a relevant feature like why do we care about this? You can observe from the definition of path decomposition that if you take any such adhesion set and you delete it from the graph, then it acts as a separator from all the vertices that live in the bags to the left of this set that we deleted and the vertices to the right of the set that we deleted. That's sort of the main meaning of these adhesion sets. They're basically nicely structured separators in your graph. Okay, so now I have to explain this theorem again. So because here we have this linear decomposition, which is basically just a fancy path decomposition. So basically, it's almost the same. So a linear decomposition is that you have a path decomposition where our path that we use corresponds like basically to this. So let's say we cut the society somewhere and we enumerate the vertices as V1, V2, V3, and so on. Right? So we make it like a path basically, VL for some L, maybe VT. And then this will be my this will guide sort of how my path looks, and I will have one bag corresponding to each vertex. So I will have some set of subsets x1 up to ht. These are my bags of the vertex set of G, such that together every vertex, so together the union forms the whole vertex set of G, and x1 contains v1, x2 contains v2, and so on. So this is how they relate to the society. This is x1, x2, x3, x4. So essentially this path decomposition goes like along this society ordering. That's what you get. And the adhesion is defined in the same way that sort of you look at these intersections of consecutive blocks. So all the rules are the same. It's basically just a path decomposition with the additional property that the first vertex lies in the first bank of the path, the second vertex lies in the second bank of the path in this order. Okay?
Yeah, but like the V2 could be also in the third.
Yeah, the picture I'm drawing are never accurate. Like I always draw disjoint things that are not disjoint, but you cannot draw things that overlap a lot. But exactly, like in a path decomposition, bags can heavily overlap because, as I said, vertices can appear in many places, right? So they can be in many different bags. But it must be sort of structured in a nice way that sort of it has to be along a path, and this guarantees this separator property that I said. And anyway, I will only need a separator property in the following, so bear with me for a second. So here's the main idea now, how we can use this. So this is what this theorem gives us, and now let's go back to the proof, because I want to finish this. So we take this geodetic cycle, and what does the fact that it's geodetic guarantee us? It in fact will guarantee us that we cannot have a large transaction. And why is this? I will only explain it intuitively, but it's easy to see from the picture. Suppose you have a large transaction like this, right? So vertices on paths that go from the top to the bottom half intuitively. Then every such path must be, because it's a geodetic cycle, of length at least a distance on the cycle of its endpoints, right? And if you have many such disjoint paths, then it cannot be that all the endpoints are close to each other, simply because these must be disjoint from each other and these must be distinct from each other. So if you have, for example, k paths, then on average, usually the path has like at least length k, because there's roughly k other intersection endpoints of paths between their endpoints. Another way to see it is that essentially the way to optimize or to minimize the sum of the lengths of the paths in such a picture is to do this picture where they sort of go parallel. You can do some uncrossing argument to prove this. And in such a case, you will get that the sum of the lengths of the paths is at least k squared divided by 2, roughly, if you have k paths. But these are vertex disjoints, so this cannot be larger than n. And so k is at most of roughly order root n. Okay, simply because if you had many of these paths, then they would take too much space in the graph, essentially. So by this result, I can put k root n here, and I will get this decomposition, this linear decomposition of my graph now applied to this cyclical ordering of the cycle that looks like this, such that the adhesion, so the intersection of consecutive bags, is at most roughly root n. Now finally, I want to use this to get a hitting set of size root n for all my longest cycles. And the idea how to do this is that you take any longest cycle in your graph and you map it to a path or a subpath of this cyclical ordering, like a...
Oh wow, because the society goes along the C.
Yes.
And C hits all the cycles.
Yes.
So every longest cycle is
yes.
a good amount of projection.
Yes, exactly.
So it's enough to hit the...
Yeah.
Okay. Wow.
Yeah. So it's I will say for everyone else. So basically take any longest cycle, it intersects some of these sets and some of them it doesn't, and project it sort of to the set of vertices of the sets which it intersects. This gives you like a sub-interval of the cyclical ordering, and we cut it, so it's actually a path, right? So you have now a set of paths along this subpath of this one fixed path, and you know that any pair of them intersects because any pair of longest cycles intersects, and a pairwise intersecting set of paths in a path has a common point. That's a well-known fact. It's a Helly property of paths, even holds for subtrees of a tree. So there will be one of these sets, for example, x4, such that every longest cycle intersects x4. And it also intersects C. And now you have to carefully sit down and convince yourself that this is true, but you can check using these facts now and these separator facts that then the set, sort of, for example, in this case, the intersection between x3 and x4 and the intersection between x4 and x5, these two adhesion sets together with this vertex here, V4, this forms a hitting set for all longest cycles. And the reason is that if you have any longest cycle, it has to use x4. If it wouldn't go through the separators, then either it would be completely contained in here, but then it has to contain V4 because it's its only chance to intersect a cycle. And if it doesn't go through the separators, then the other option is that it's completely outside of it, but then it doesn't hit x4, so that's a contradiction. So basically, that's how you get a separator, and this is just 2 times another constant factor, root n, basically. So that concludes this proof. Yeah, so let me finish with some final words. What I couldn't say now, there's actually a big part of this paper that I didn't explain now, that is roughly as more in length actually than what I explained so far, which is to prove another upper bound for this LPT and LCT. So here I showed you the proof for LCT at most root n. It also works for paths, but you need some extra argument. But you can actually prove also in terms of the length of the longest cycle an upper bound on the hitting sets. So now this was in terms of the number of vertices. We have an other upper bound that says that for any connected graph, this LPT of G is at most O of L to the 5 over 9. Is that Fibonacci? Probably not.
9 is not Fibonacci.
Yeah, where L is the maximum length of a path in a graph. So this is better if you have a graph that doesn't have very long paths. And the way we prove this, just to one comment, I mean, I don't have any time to explain it, is basically to say that in this case where we win, so here we win by saying if I have a large transaction, then I will get many vertices in the graph.
Wait, L is the longest path or something?
Longest path.
Okay, makes sense.
So the way we prove this is that we say that in this case of the proof where we say, large transaction gives us many vertices in the graph because they take up much space. In fact, you can be much more clever and look at this complicated picture of how this basically matching of paths looks here and traverse many of them with some other path, which will give you a very long path. Instead of just many vertices, you will get a very long path. And this is also quite complicated, actually, how to prove this. So this is an additional argument that I cannot show now. But using this additional argument, you will get an upper bound on the longest path traversal in terms of the longest cycle. Longest path length. Sorry, that I'm confusing these things. For cycles, actually, it doesn't work in this picture because, for example, this picture, when these things are all parallel, you will not find a cycle that uses more than 2 of these crossing paths. So cycles are a bit more difficult in this setting. Anyway, there's some more calculation to be done, but basically using this upper bound, you then can further improve the lower bound for this original Lovász conjecture, because the logic is that, well, if L is already very long, we're happy, and if L would be too short, then we would get a small hitting set, but then by this argument that we always have a cycle of length at least n divided by the hitting set, we will again have a long path. So it's a kind of a weird maximum thing. And so we can slightly more improve this lower bound for Lovász, so we get omega of n to the 9 over 14 for Lovász. This is roughly n to the 0.643. So still not amazing, but better than before. And as I said, also for this approach, so you can also try to push this what we do here in the proof further, try to find even longer paths in these kind of structures. And then you have the same limit to this approach than the other method I showed you, which is n to the 2/3. And what I'm really excited about would be to combine both proof approaches that I showed you so far. So this is completely independent from this other intersection of 2 longest cycles approach I showed you before. And it's not obvious to me why you cannot combine them. I mean, it's also not obvious how to combine them, but there is a chance that you can combine both approaches and then beat this n to the 2/3 barrier and get even closer to n. And this is what I will probably at some point work on in the future. But yeah, so let me finish here.